Welcome everyone. In 7.2 we're going to talk about volumes of revolutions, disks and washer methods. And let's take a look at what we're dealing with here. So suppose we have some continuous function f on the interval from a to b. Okay, we know that we can find the area between the graph of f and the x-axis by integrating f from a to b. What if, on the other hand, we were to take the region bounded by f and the x-axis on that interval and we were to rotate it about the x-axis? Okay, so we're basically going to flip this thing around the x-axis and we're going to get a three-dimensional solid that would be formed here. Okay, and ultimately we want to be able to find the volume of that thing. All right, so think about what's going on. All right, so like if I were to take this point right here, the point B, f of b, and I were to rotate that around the x-axis, right, it would make this circular kind of shape. All right, and in fact, if I were to take any point on f and rotate it, I would get this circular kind of shape. All right, keep doing this all the way to the end, and we get these series of circular disks, as they're called, okay? And we would do this throughout the region. So the way I typically draw these is basically at some point, it would be a 180-degree rotation about the axis or a mirror image. So I typically try to visualize these things by drawing the reflection over the axis. And then I'll draw in some circles to represent what's going on here. And again, we have these series of disks, okay? Think of this as a really, really thin, like almost like a quarter or a sheet of paper in the shape of a circle that creates this thing that we call a disk. Okay, but this region is made up of an infinite number of these paper-thin, infinitesimally thin disks. And this is how I typically draw these regions, okay? And now the idea is kind of having an understanding that we're dealing with this particular shape. Basically, if I were to take and slice this thing in half right here and then rotate it and look into the side, I'm still going to be looking at what shape. I'm going to be always looking at some sort of circular shape as I look in from the side of this thing, okay? And again, those are called the disks, and so the way we think about this is again, there's an infinite number of these disks stacked together that create this solid region. I mean, think about sheets of paper stacked together. One sheet of paper is pretty darn thin, but if you put a whole bunch of sheets of paper together, you have some thickness, right? That's how books are made, right? So this is the idea, and what we basically do is we find the volume of each of these infinitely many disks, and we sum up those volumes to get the volume of the entire region. Okay, it's a lot like using integration to find area. We think of the area under the curve as an infinite number of rectangles, where f of x represents the height, dx represents the infinitesimally thin width, and so when we integrate f of x dx, we're getting base times height, and we're summing up the areas of an infinite number of infinitesimally thin rectangles, giving us the area. It's the same idea, but now we're extending that to volume. Okay, so let's talk about these things. Let's talk about like a disk. Okay, so I've got this thing right here. I've got this disk. Okay, and let me kind of bring it over here, redraw it. Okay, now again, it's very, very thin, but it does have a little bit of thickness, just like a sheet of paper would. All right, so this is me trying to show like the thickness here. Okay, or back on the original diagram, here's this. Okay, so there's my thickness that I'm kind of shading in blue. And if you think about it, it kind of looks like a quarter, right? It's circular, it has a very little bit of thickness to it, like a dime or a quarter or a coin. And so what kind of shape do we get out of these? Well, we get little cylinders, right? They're little quarters or little cylinders. And what's the volume of a cylinder? Well, that's pi r squared h, okay? Pi r squared h gives us the volume of these cylinders, okay? Get rid of the purple stuff. I'm going to focus on some things here. So in terms of, the function that we're dealing with, right, we've got this arbitrary function f. How do we come up with the r squared and h to sub into this formula, and how do we get this stuff? Okay, well, what is the radius on this thing? If you think about it, the radius goes from the center of the circle to the edge of the circle, right? And so at any point along this series of disks, the way this is drawn, the radius is nothing more than going from the x-axis up to the function. So for example, if this particular purple disk right here, if this is up at y equals 2, the radius of that thing is 2, right? If this is up at like 2.5, the radius here is 2.5. The radius is nothing more than the y value of the function itself, all right? So I can sub that in for r here. The function value gives us the radius of that particular disk at whatever x value we're at between A and B. And the thickness now, it's like the cylinder's on its side, but that's the height. That's the thickness, if you will. All right. And this tiny little bit of thickness over on the original diagram, we write as dx, or sometimes we write it as delta x, okay? But subbing back into h over here on the right, we now have a volume formula for one disk at one x value. So basically we plug in the x value, get the y value and square it, and whatever our delta x is or our dx is. Okay, very, very small value, 0.001 or something like that, okay? In theory, okay? But again, what we do now is we let the number of these things go off to infinity, and we let them get very thin, all right? So what do? Well, here's the formula for the volume of a single disk, and if I want to add the volumes of all these disks between A and B together, that's where the integration function comes in. So at the end of the day, we get volume equals the integral from A to B of pi f of x squared dx. And often what I'll do is I'll bring that coefficient of pi out front. So I write the formula like this: pi integral f of x squared dx, which really represents pi, your radius squared, times your height. Okay, and that will give us the volume of a region below a function above the x-axis that's been rotated about the x-axis. Okay, so that's one formula, and I'll summarize at the end, and then we'll do a bunch of examples so you see how this stuff works. But I'm going to continue on here with a couple more formulas we're going to look at. Okay, so I'll leave this one down below, clean up this a little bit. And the next thing we're going to talk about is, well, what if instead of rotating one function about the axis, we are rotating the region between a couple functions? So we just had the lesson on area between curves. And so now we're going to take a region between curves and we're going to rotate it around the x-axis, okay? So there's my original f, okay, still on the interval from A to B. And let's suppose, we have this other function that I'm going to call g coming in underneath it here. Okay, so there's the g function. Now my region is the region between f and g on the interval AB. Okay, so again, I want to take that region and I want to rotate that about the x-axis. Okay, just cleaning this diagram up a touch. Okay, and so now look, again, I'll draw it like this. Here's the mirror image of the green function. This would create its own set of circles or disks. Let's get the f function coming into play here. Okay, and then this would create its own set of circles as you rotated that function. Okay. And what do you notice now? Well, basically, we have kind of like a hole going through the middle of this thing is what you want to try to be able to visualize here. Okay, I've got this purple function kind of going through the center. That creates those disks. Okay, and then I've got this blue function here. And again, the original region is this, so this is the only part that's being rotated, right? And so we've kind of got like this big hole in the middle of this thing, all right? And so if we examine this and we kind of look at it straight on here, we're looking at something like this from the end, and it's got that hole in the middle, and this is what we call a washer. Okay, like many of you have probably seen little metal rings that are called washers before, and this is the idea, okay? So what if I wanted the volume of this strange solid that was created? It's really just a play on what we just did. Basically what I'm doing is I'm finding the volume within the larger set of disks, which would be all these. From that, I'm going to remove the volume inside the smaller set of disks. That's basically everything inside of the purple one, okay? So I'm just subtracting everything inside the larger disk minus everything inside the smaller disk. So the volume for washers is going to be basically, well, it's the larger one, pi integral a to b. The way I've drawn this, f is the larger function. So that's all the disks inside the blue f function minus all the volume given by the disks inside the g function. Since both the coefficients and the bounds are the same, and I'm using subtraction, I can combine this into a single integral. So the volume becomes pi integral a to b, quantity f of x squared minus g of x squared dx, where f is the larger radius created and g is the smaller radius created. Okay, f is my bigger radius here, g is my smaller radius here. Okay, and again, we'll see some examples of this, but again, it's just a play on the whole disk formula. All right, and then last but not least is when we take a region and we revolve it around a horizontal line other than the x-axis. Okay, so give me a second to set that up here. Just kind of get rid of all this. And again, I'll summarize all the formulas at the end here, and then you'll see it in action when we do an example, okay? So, suppose again I have, some region here. Here's f. Here's the interval from a to b. Here's some other function g. Okay, and now let's suppose like I rotated around this line at y equals k. Okay, some just arbitrary horizontal line. Okay, so now, again, if I draw the mirror image, it's going to look something like this here. Do my best. Okay, something like that. And look, still I'm getting these washers here. Okay, I've got that larger set of discs there. I've got a smaller set in between. So certainly we're going to get the washers here. All right, and it's exactly the same concept. But what's different is how we get the radius of these circles or these discs. Okay, so look, I mean, by definition, the radius of a circle goes from the center of the circle to the edge. All right, so there's my smaller radius right there. Well, how would I compute the length of that? Like, I would have to know the y value here on the g function, and I would have to know what this y value k is. I mean, and then I would just do what with those two numbers to get this length? Like, for example, if that's up at 2 and that's down at 1, what's the size of that radius? Well, 2 minus 1 is 1. You're just subtracting the 2. So the smaller radius is just given by g of x minus k. Right? If the value of g was up at 2 and the line of rotation is at 1, we subtract those to get the value 1. Same thing for the larger radius. Let me just draw a bigger circle in here. Here's my larger radius going up to the larger function. Well, again, it's just the difference in this y value and that y value. So it's given by the f value minus the line of rotation. Again, if f is up at like 5, just to make up numbers, and then the line k is at 1, that radius is 4. 5 minus 1, this f value minus the line of rotation. Okay, so to kind of summarize everything, putting it all together. Summary of our formulae. All right, so the basic, the volume of disks around the x-axis, pi integral a to b, take your function, square it, dx. This is about x-axis. If we have a line of rotation, y equals k, we do this. Again, when we subtract, this is how we compute for the radius. It's the same concept. Radius squared times dx. We just have to be careful how we're computing the length of the radius of each of our disks. And that's how that's done, okay? And then for washers, it was the difference between the two. So again, the basic form looks like this. This is about the x-axis when we rotate about the x-axis. And again, if we rotate about an arbitrary line, y equals k, we adjust for that in our radii. So here it's f of x minus k, quantity squared, that represents the larger radius, minus g of x minus k quantity squared, that represents the smaller radius. Okay, and with a little bit of practice, you know, you'll get these down. Okay, I think they seem worse than they are, but hopefully you get the concept. All right, so we're going to do a bunch of examples, and hopefully, you know, you get a sense of how this stuff works. Now, in addition to being able to do these with respect to x, of course, if we now rotate around a vertical line, as you'll see in some examples, we can also integrate with respect to y. So we need to be careful. Okay, but let's take a look at some examples and see how this stuff goes. Okay, so I have one region. We'll do a bunch of examples with this one region. To see a bunch of different things here, okay? So let's have R be the region in the first quadrant, bounded by the line x equals 3, that's the vertical line on the right, and the curve y equals e to the x minus 1, that should say. Okay, and so we get this little region in the first quadrant created by these things, okay? Part A, for review, let's find the area of R. Now, in this lesson, I'm much more interested in setting up the integrals. On your homework on WebAssign, you may need to actually find the value of them. So you're going to use, you know, your Math 9 feature on your calculators. Use the integration feature on the calculator to get final answers, okay, if you need to do that. But we'll focus on the integral setup mostly in this lesson, okay? So for part A, find the area of the region. Well, I can certainly integrate with respect to x from left to right. I have the blue function on top and the x-axis on bottom, and it looks like we're going from 0 to 3. So the area is nothing more than the integral from 0 to 3, e to the x minus 1 dx. And again, you know, if I had to, I could do this out by hand just for practice. I will. Integral of e to the x is e to the x. Integral of negative 1 is negative x. From 0 to 3, so we're going to get e cubed minus 3 minus e to the 0 minus 0. Be careful, what's e to the 0 equal? That's 1, right? Anything to the 0 power is 1. E cubed minus 3 minus 1 is e cubed, let's see, negative 3 minus 1 minus 4. Okay, and again, you could also just use a Math 9 feature on your calculator to punch that in, and you'll get some, you know, decimal equivalent. Okay. Part B, revolve R about the x-axis and find the volume of the solid formed. Okay, so for each new part, I'm going to redraw the diagram specific to what's going in that part of the problem. So we've basically got this, and I'm revolving about the x-axis. So right around this thing. So there's my mirror image, and when I draw this in, really, the only thing being rotated, so to speak, is this blue function. There's no other function in between. So what we have here are some disks. Okay, that's the first thing I realized. And these are oriented from left to right, just like I drew up in the concept portion of the lesson above. These are tiny little dx's. So these are what I call dx disks. All right, and we're revolving around the x-axis. All right, that's the line y equals 0. Okay, in terms of the formula above, that's k equals 0. So these formulas work even around the x-axis. You can always use these versions if you choose, okay? But in any event, we got disks with respect to x. So we got bounds from 0 to 3, and the formula is volume equals pi integral a to b f of x squared dx. So here, pi integral 0 to 3, our function, this blue function, was e to the x minus 1 quantity squared dx. And this isn't something that we're going to work out by hand. Again, the focus is, for the most part, going to be on setting these integrals up. Okay? And if you needed to, you could very carefully punch these in to get their values. Okay? So there we have it. This is an integral that would give us the volume of that region. All right, now let's take the same region and revolve it around the y-axis and see how things change here. So I'm going to draw it like this. I'm going to set my axes up like this because this now is the axis I need to revolve around. Here's that e to the x minus 1 function. Here's x equals 3. Okay, but again, this time I'm wrapping it around left to right, around the y-axis. So here's the mirror image of the blue function. Kind of. I'm not the best artist. Here's the mirror image of the purple function. And now when I wrap, look, I'm not going to draw it right up here at the top. I'm going to kind of come down here. But when I wrap the blue function, I'm going to get this set of disks. When I wrap the purple function, I kind of pick the same vertical value here, and I wrap around, and I can see that I now have washers. Okay, I have this big hole in the middle of this region, and we're dealing with washers. So that's a little different than the last one. And what else is different is the orientation of these washers. This is the very thin thickness this time. Okay, when the thickness looks like this, that's a very thin thickness left to right. That's a dx. This is a very thin thickness up and down now. This is a dy. So we're going to have to integrate with respect to y here. So the bounds are going to be with respect to y. The lower bound starts at presumably 0. The upper bound is where what happens, these two things intersect. So I got to figure out what that y value is. Okay, this is at x equals 3. Okay, that's the y value is 0 there. Okay, and I want this y value up there. So how am I going to get the y value of the point of intersection? Well, I want to know, basically the blue function is e to the x minus 1, and the purple function is x equals 3. So what's the y value when x equals 3? And that's going to be e cubed minus 1. So just some arbitrary y value that we're going to call, well, not really arbitrary. It's a specific y value. Just looks kind of weird. It is what it is, though. So I plugged x equals 3 into the blue function. There's the upper bound at e cubed minus 1. Okay, so we are rotating around the y-axis, which is x equals 0, so we are good there, but we're doing washers, so volume equals pi integral a to b, larger set squared, and actually I got to write it with respect to y here. I'll write it as f of y squared minus g of y squared dy, okay? So let's set some of this up. We're going to go pi integral, 0 is the lower bound, e cubed minus 1 is our upper bound there. All right. We're going to have some function squared minus another one squared with respect to y. Now where we got to be careful is what we're plugging into these quantities. Okay, we need functions of y. That means x by itself in the equation. Well, the larger set of circles is created from that outer function at x equals 3. That is already in the form of x equals. We literally just plug that in, okay, 3 squared, okay? In fact, every circle is the same size, right? It starts at 3. Every one of these circles all the way up has a radius of 3, and that's what that represents. Okay, for the other one, the inner function, the blue one, here's where we got to be careful, okay? The blue equation is, let me just find kind of a good place to do this, y equals e to the x minus 1. So again, we got to get x by itself as a function of y. So I'm going to add the 1, and now what are we going to do? It looks like we're going to take the natural log of both sides to get rid of the e, okay? And this now is how we represent the inner function. And there we have it now. As ugly as it may look, this is an integral that would give us the volume of that region. Okay, pi integral 0 to e cubed minus 1 for the y bounds going up and down. We've got the larger radius x equals squared, the smaller radius of the form x equals in terms of y squared. Okay, and that's the gist. All right, and again, with some practice, these things end up not being too bad. Okay, they look uglier than they are. Revolve r around the line x equals 3 and find the volume. So this time we're now going to rotate around a vertical line that's not one of the axes. We're rotating around x equals 3. So let's see how this works. So again, here's kind of like the original region, but I'm going to go to the right a bit. So here's my e to the x minus 1. Here's x equals 3 right here, and this now is our axis of rotation. So when I rotate this vertical line, it's not going anywhere, but now the mirror image of the blue takes me over here. And again, now if I draw, I'm going to have a set of solid disks this time. And how are these disks oriented? It looks to me like they're low to high. When they're low to high, integrate with respect to y. Okay, same orientation as the previous problem. Okay, so again, integrate with respect to y from low to high. Now, fortunately, we already figured out what these values were in the last problem. Okay, and now let's see, though, how this comes into play. So we have disks. and we have a line of rotation other than an axis that we revolved around. So here's the version of that formula. And again, I got to be careful because we're integrating with respect to y, so I just want to write it like this, okay? So here we have volume equals pi integral low to high. Our function of y is still that, all right? We already came up with that. That's x equals, what was it up above? ln of y plus 1. Okay, so that's what we're plugging in. That's still the same equation here. Minus the line of rotation at k, which in this case is 3. Okay, and think about it again. If I want the length of the radius of one of these disks, it's this value at 3, right, minus that value over there on the function. I'm just finding the difference in those x values. That's exactly what this quantity represents, okay? And what do I need to do to that quantity? I need to square it, and there is our integral that would then give us the volume of that region. Okay, so again, pi, radius squared, dx, dy, whatever it is you're talking about. Okay, let's take the same region, and now we'll move the axis of rotation to the right a little bit from the previous example. So there's at x equals 3. And now I'm bringing the axis of rotation over to x equals 4. So I'm going to draw it like this. All right, and so when I do the mirror image, now this is over here. Blue function's over here. When I wrap the purple, I'm going to get a set of circles. When I wrap the blue, I'm going to get a set of circles. And we're back to washers now. Again, these are dy washers. They're being stacked low to high. So we're going to integrate with respect to y. When they're stacked low to high, integrate with respect to y. When they're stacked like pancakes, okay? When they're oriented more like left to right, or like records in their paper sleeves. If you guys go back that far with that kind of stuff, you know, that's when you're integrating with respect to x. Okay, so try to see the difference in the orientation here. In any event, so we've got washers, and we've got an alternate line of rotation at x equals 4. So volume equals pi integral a to b. Formula is going to be f of y minus k squared. That's the bigger set of radii, minus g of y minus k squared for our smaller set of radii, dy. All right, subbing in. Bounds, we know are 0 to e cubed minus 1. Here, we're going to have a big radius squared minus a smaller radius squared. Just kind of setting up my template. What are we subtracting? What's the line of rotation here? X equals 4. So I know I'm going to have a minus 4 in the back of both of these parentheses. And now I need to identify the two functions. Well, again, careful. Which one's giving me the larger set of circles here? It's the blue one. So that was x equals ln of y plus 1. So that's going to be the larger one. So that'll go first. And the smaller one is the purple function. And that's given by x equals 3. So the 3 will go in there. And then we just get -1, quantity squared. Think about the size of these purple circles. Notice they're a constant radius of 1, right? Isn't the radius always equal to 1? Now, we got -1 in here. We're not being careful with the order of subtraction, and we don't need to be, because what are we doing to these things? We're squaring it. So whether it came back +1 or -1, when we square it, it's going to come back the same value. And so we don't really need to be careful about the order of subtraction with these. And so point being, you can always take the function minus the line of rotation. Squaring the whole quantity is going to make it absolutely correct, okay? So that's the idea here. You could clean that up a little bit if you wanted to and just make that -1 at the end of the integral. But on the AP exam, you can leave it just like that, typically, unless they say you need to punch it into your calculator, okay? So again, you know, take your time with these. It's going to take a little practice, I think, both getting the drawings down and really getting the idea of discs, washers, and these lines of rotation. Okay, take a look at a couple more here. Revolve about y equals -1 and find the volume. Okay, so I'm going to draw it like this. let's see here. So here's the original e to the x minus 1. Here's x equals 3. Now we're going to revolve around the line y equals negative 1. So that's a horizontal line down here, and there's the axis of rotation. Okay. And so, kind of drawing this mirror image here. Get this, we get that. Okay. And let's see, the blue function is going to give me this set of circles. And if you think about it, we're going to get a set of circles here when the original axis rotates. The purple one kind of just sets up our bound. Looking at the orientation of these are stacked left to right. We're going to get dx washers from 0 to 3 again. Okay, so we're going to integrate with respect to x. We've got an alternate line of rotation, and we've got washers. Volume equals pi integral a to b. It's going to be the larger radii squared minus the smaller squared dx. V equals pi integral from left to right, 0 to 3. Okay, we're going to have something squared minus something squared. And what am I subtracting? Now I'm subtracting negative 1. So I'm going to have minus negative 1 at the end of both of these parentheses when I sub that in. Minus negative 1. So plus 1. Now for the larger function, bigger circles are coming from this original blue function. That's e to the x minus 1. Okay, smaller circles are actually coming from this. Okay, it's actually coming from the original x-axis. What is the equation of the x-axis? Y equals 0. That's right. And plug that in, and that's absolutely correct. There's a constant radius of 1 for these smaller circles, and yes, that is correct. Every one of these smaller circles will have a radius of 1 because it's this horizontal line revolved around that one. Okay, so hopefully you're seeing things come together, but if you have questions, obviously reach out to me, okay? And again, we could clean this up just a little bit if we wanted to. Why not? Looks like the first quantity just becomes e to the x squared, and then this is just 1 minus 1. We could even make that e to the 2x if we wanted to. Okay, again, if you had to punch it in to get a final answer, do so carefully. If you have questions about that, reach out to me. Okay, one more example. Revolve the region about y equals e cubed minus 1 and find the volume. Might seem like an odd value, but remember that was really just at the top of this original diagram. So there's that. There's that at 3. And y equals e cubed minus 1 was this point of intersection up here. So the line of rotation is this. And now we're kind of flipping upwards this region. Okay, so let me get the blue in place. And let me get the x-axis rotation there. And again, careful here. It looks like we're going to have a large set of circles created by the axes. We're going to have a smaller set of circles created by the blue function. And again, we end up with these washers. Okay, so sometimes the axes themselves act as things that are rotated. And again, now we have orientation from left to right, so we're dealing with dx washers with a strange alternate line of rotation. Let's set it up. Volume equals pi integral a to b, bigger radii squared minus smaller squared dx in this case, bound 0 to 3. Okay, I'm subtracting e cubed minus 1. Careful with all these parentheses. Okay, I'm subtracting those, e cubed minus 1, from, okay, larger circle actually came from the original x-axis. This is the biggest circle. And again, that's just the line y equals 0, so that goes in there. All right, and then the smaller one came from this original blue function, and that was your e to the x minus 1 function. Close that up, put a dx at the end, and there we have it. Again, let me clean this up with the parentheses a little bit. It's this whole thing squared and this whole thing squared. And all this other stuff is just inside there. Okay, folks, so that's the gist, okay? So try those homework problems. Important thing is getting those integrals set up and then, punching them in very, very carefully using the graphing calculator or perhaps some other online site that you know about. All right, if you have any questions at all, reach out to me and have a good day.